Hello, everybody, and welcome to our first video in our thermodynamics unit. So some of this stuff might be familiar to you already because I do talk about thermodynamics a little bit in Chem 2. The extent of thermo that I cover kind of depends on the semester, but I do always talk about a little bit of thermo at the very least to kind of prepare you for this. So my hope for this unit is for us to kind of go through this relatively quickly because we typically spend a little more time in some other units. But let's go ahead and first talk about what is thermodynamics. Okay, you might be familiar with the word thermo. You think of thermometers, you think of heat. And that's exactly what we're talking about in thermodynamics. This is a branch of chemistry that deals with the heat absorbed or produced in a chemical reaction or a physical change. So we can have heat that is absorbed or released when we go through all different types of chemical reactions, or if we go through physical changes, and that includes dissolving something in water, let's say making a solution. And there's two types of reactions that we have to be familiar with, and those are exothermic and endothermic. So let's get the pen out here and talk about what each of these means. And remember, in Chem 2, we did talk about these a little bit. If you have an exothermic reaction, so if you think what exo means, exo typically means on the outside. Exothermic reactions will release energy to the environment. So these release energy to the environment or the surroundings, you can say. Either one is fine. And when you have a reaction that releases energy to the environment, it tends to feel warm. Whereas endothermic reactions, endothermic is the opposite. This is when we have energy that's absorbed, absorbs energy from the environment. Spelling things wrong here. And when energy is absorbed from the environment, it's taking energy from the surrounding atmosphere, usually the air, and it's bringing it in to itself. Now, if you put your hand on something that's absorbing energy, it's going to tend to feel very cool. So this will feel cool or cold, doesn't matter. Feels cold. So when you go to the doctor, let's say, and they give you a shot and they put that alcohol swab on you, that alcohol swab tends to feel very cold. Why does it feel cold? That's because that alcohol is absorbing energy from your body in order to vaporize. And when that happens, it tends to feel cold. So two types of reactions, they are exo or endothermic. Every type of reaction is going to be either one of those two types. The extent to how exothermic or how endothermic might be very slight, however. Something might be slightly exothermic, which means it might not feel that warm. So just something to keep in mind. Now let's talk about what enthalpy is. So a word we haven't really talked about yet, but for us, it tends to just mean heat, right? So let's go ahead and get this color out that I like to work with. So the enthalpy of something is the total heat content of a system at a constant pressure. So for us, okay, now if you remember back to Chem 2, we talked about Q, where Q is equal to heat. Now, in this unit, we're going to use Q, but we're also going to use H. At this point in your chemistry career, the terms enthalpy and heat can be used interchangeably. The reason why is because this is always going to be at constant pressure right here. Enthalpy is the total heat at constant pressure. if the pressure is not the same, which it's not when you get to upper level chemistry classes, enthalpy and heat do not mean the same thing. But for us, since we are always working at a constant pressure, we can assume that enthalpy and heat mean the same thing. Okay, so just keep that in mind. You wouldn't get to the difference in that until you get to like college level physical chemistry classes, which are like 400 level classes, which I'm sure many of you wouldn't have to take unless you're actually majoring in chemistry. So the change in enthalpy of a reaction is represented by the delta H. So you might remember whenever we use the change in something, the change is always represented by the triangle. So like change in temperature, we use the triangle, and that's delta. So the change in your enthalpy of a reaction is represented by delta H, and this is used to describe both physical and chemical processes in chemistry. So we could have reactions that are going to have a change in heat or enthalpy, but we can also have physical changes. Like we said, making a solution could result in a change in enthalpy as well. And the way we can calculate enthalpy is by looking at the total energy of your products minus the total energy or the total heat of your reactants. We're going to look more at this a little bit later in the unit, not so much right now, so I'm not going to harp on that. And what we're going to find is that as we're going through these heats of reaction, okay, so heat is what we call an example of a state function. And a state function means that this is path independent. I always like to bring this up. This is an upper level type of chemistry thing, a state function, but it's always good to kind of talk about, and we're going to see more of this later in the unit. So consider going up a hill or going up a mountain. You're hiking up a mountain. Okay, there's two paths to get up the mountain. Path number one, a little bit easier, right? But takes a little bit of a longer time, right? However, path number two, we see goes directly up. It's a shorter path, but it takes a lot more energy for you to hike directly up the mountain. Both of these routes, okay, get you the same exact distance. So they're still going to get you from point A at the bottom of the mountain to point B. But they're two totally different routes you can take. Okay, so regardless of how you get from A to B, the distance from A to B is always the same. It is path independent. Okay, and we'll talk more about that, like we said, as we get to actual reactions. Let's talk about some examples of endo versus exothermic reactions. So here's an example, melting water. So I have water in the solid phase becoming liquid water, so it's melting. And we'll see that a lot of times in reactions, we haven't really talked about energy content yet. We're going to start introducing more of energy now. But in order for water to melt, right, we have to put energy in because solids have vibrational energy only, whereas to become a liquid, I have vibrational and translational energy. Oh my goodness, translational. Translational means it could slide past each other. So in order to gain that extra energy, I have to input energy, right? I have to warm up the ice. I have to add heat in order for this to happen. And you'll see that my delta H in this example, my change in enthalpy is a positive value, okay? Positive value means that this has to absorb energy for this to occur. So because melting water has to absorb energy to become a liquid, water is an example of an endothermic process, or melting water is an example of an endothermic process. And this is because heat must be applied to the system, or heat must be absorbed by the ice in order for this phase change to occur. If we are condensing water, right, let's take a look. I go from a gas to a liquid. Gases have vibrational energy. translational energy, and rotational energy. Whereas liquids have just vibrational energy and translational. So they're losing that rotational energy. As they lose that rotational energy, it's got to go to the surrounding environment. Okay. So energy is a product when we condense water. So therefore, if I look at my delta H, my change in enthalpy, notice how I have a negative sign in this case. And that negative sign means that energy is released in this process. So energy is a product. So condensing water is an example of an exothermic process because heat is released in order for this phase change to occur. Both of these two, so melting water and condensing water, are both physical changes. However, we will also see this occur with chemical changes. So for example, the decomposition of water. If I look here, notice how my value for delta H is positive. This must mean that I have to input energy to my reactant side. Energy is a reactant here. And I have to input 116 kilocalories of energy in order for this decomposition to occur. Because energy is a reactant and this value is positive, the decomposition of water is an endothermic process. Whenever energy is a reactant, it is endothermic. Whenever it is a product, it is exothermic. And a lot of times we can look at the changes in energy by looking at a graph. And normally your graph looks something like this. We have your enthalpy, which is always represented on your y-axis. And we have your process of the reaction, or progress. I like progress better. Progress of reaction on this time. So we could say time, in this case, might be increasing as I go across. Your reactants have some amount of energy, okay? Your reactants have some amount of energy. In order to get my reactants to become products, we have to input some amount of energy first. So notice that I have this curve going up here towards the top. So it's going to you have to input a little bit of energy first, and we call this the activation energy, which we'll talk about a little bit later in this unit. Once we get over that hump, once we have added enough activation energy to get this reaction started, you are going to have some amount of energy that's associated with your products. So notice how my products is lower than my reactants. Because the energy or the enthalpy of my reactants is higher than my enthalpy of my products, products minus reactants is going to give me a negative value. So in this case, this is an example of an exothermic reactance. Your products have less energy than your reactants. And if I look back up here, if products is less than your reactants, you are going to get a negative value for delta H. This represents an exothermic reaction. Whereas if your reactants is lower than your products, so notice the opposite here, reactants is higher than products. Here I have reactants is lower than products. I still have to get over this initial activation energy. I still have to put some energy in to a reaction. However, the difference from reactants to products is from here to here, but my products are greater than my reactants. If products are greater than my reactants, my delta H is positive, which means it is an endothermic reaction. So all we have to look at, let me get a different color here to try to represent this. We have to look at the difference from your reactants to your products. The difference from the reactants to the products. That's going to tell me my delta H. Depending on if my reactants is greater or less than the products tells me if it's negative or positive. We're going to work more with this throughout this unit as well. Just wanted to introduce this here to you now. Let's go ahead and take a look at some thermochemical equations right here, which we already started to look at on this last page here. So a thermochemical equation, delta H is typically included as a reactant or a product. For endothermic reactions, we already said that delta H is a reactant. And for exothermic reactions, delta H is written as a product. So what we're going to do is we're going to write the thermochemical equation for the 3 examples on the previous page. Okay, so we're going to take these ones here and we're going to write the thermochemical equation just by adding delta H in to where energy is located. So if I look at melting water, number 1, okay, this particular delta H we know is a reactant because I have to input 335 joules of energy in order for this reaction to occur. So I'm going to write this as 335 joules per gram of energy plus solid water, also known as ice, is going to give me liquid water. So in order for me to melt 1 gram of water, I would have to input 335 joules of energy. If I were to melt 2 grams of water, of course, this value would be double that. So we're going to manipulate these with amounts a little bit later in this unit as well. Let's take a look at 2. So this condensing of water right here, delta H is a negative value. So because this is a negative value, this is how much energy is released, which means that this 2,260 is a product here. So I'm going to rewrite this as a product. So if I have H2O gas, that's going to become water. But in this process, I would liberate 2,260 joules per gram of energy. Okay, sometimes you might see heat written as an actual reactant or product, and that's exactly what we're doing here. And for this last one, so for the decomposition of water, it looks like 116 kilocalories is equivalent or is our reactant here. I have to input that much energy because delta H is a positive value. So we're going to say 116 kilocalories plus 2 water molecules would decompose into 2 hydrogens and an oxygen. Different ways of representing the same exact equation. I feel like we've been doing some FRQs and you've kind of seen some of these already. You've especially seen delta H like is represented up here. We've kind of ignored that so far because we didn't talk about this yet, but that's what that means. It's just how much heat is either absorbed or released in the reaction. On that note, I want to talk about Hess's law, and this kind of brings us back to the state function part. Hess's law is one of the last things that's typically covered in this unit. I like to talk about it first. I don't know why, I just do. But let's go ahead and get Hess's law down. I think Hess's law is pretty simple, actually. It looks a little tedious, but not too bad otherwise. So what is Hess's law? Hess's law is the overall enthalpy change reaction is the same regardless of the pathway or the number of steps it takes. So this is kind of like where I was going talking about what a state function is, right? So if I look at this first example that's represented here, so it doesn't matter how I get to the products, the overall energy change is going to be the same regardless of the pathway or how many steps you take. Delta H is the same regardless. So if I take a look at this reaction up here, okay, nitrogen and oxygen tend to form nitrogen dioxide, okay? And this delta H is 68 kilojoules. So I would have to input 68 kilojoules in order for this reaction to occur. However, we're going to find that reactions don't always occur in one step. Okay, this is a kinetics thing. We'll talk about kinetics last. This reaction actually occurs in two steps. The first step says that nitrogen and oxygen will react to form two nitrogen monoxide molecules. And this reaction, we have to input 180 kilojoules of energy. However, we didn't actually produce NO2 yet, but the second part of this reaction says that those two NO molecules combines with another oxygen molecule, and that makes the two NO2s. And this process releases negative 112 kilojoules of energy. If I find the sum of these two reactions, kind of like what you did with net ionic equations, canceling stuff out, if I compare these two, all right, looks like I have 1 and 2 in my reactant side, so and none over here, so that's fine. O2 in my reactants here, I don't have any O2s to cancel there. Looks like I have two NOs that is a product of one reaction, but a reactant in in the second reaction, so those cancel out. And it looks like I have 1 and 2, which is represented here, and two O2s, and this gives me 2 NO2. The sum of those enthalpies is going to give me the enthalpy of this reaction. So 180 plus negative 112 will give me positive 68. So this reaction, the enthalpy of that reaction is the sum of its individual reactions, regardless of how many steps it takes, okay? The delta H is the same regardless, 68. You could try to find delta H's for a reaction like this that's going to be 10 steps long. Your delta H should still be 68, regardless of the pathway that it takes. So here's some graphs that kind of represent this. So enthalpy, reactants, we always go from A to B. The difference so the enthalpy of my reactants and the enthalpy of my products. Products minus reactants gives me some enthalpy. Sometimes, you might have a multi-step. So this would be a one-step reaction. Sometimes reactions occur in two steps, like we represented up here. You might have an intermediate. And in this case, an intermediate is something that was made, but then it's used up again. So in this case, that would be those two NO molecules as an intermediate. The enthalpy is still the difference between your reactants and your products. It's always reactants to the products. This right here doesn't matter, okay? Enthalpy is always products minus reactants, okay? So notice how regardless of pathway, if it happens in one step or if it happens in two steps, the difference is always reactants to the products. This is what we mean by a state function, okay? Here's a specific reaction. So the combustion of methane typically occurs in two steps, okay? Here's my reactants up here, and my products are all the way down here. So if this reaction happens in two steps, here's my reactants and here's my products. My first step looks like it releases 607 kilojoules, and my second step releases 208 kilojoules. My total enthalpy change would be the sum of those two, negative 890 kilojoules, because it's always reactants to products. That's the enthalpy of our reaction, okay, is the difference between reactants to products. If products is lower than reactants, we know this is an exothermic reaction, and we can tell because my enthalpy is, or my delta H is negative. Same thing here. Products is lower than reactants. This must mean for both of these ones that your delta H is a negative value, okay? Because products are lower than reactants. Let's go ahead and do some examples with Hess's law. So, considerations. I'm going to take you through this here and we'll talk about how to do this. So, sample problem 2. Two forms of carbon. You have graphite and you have diamonds. Okay, very different properties. Using the enthalpies of combustion for graphite and diamond, calculate the delta H for the conversion of graphite to diamond. So using the enthalpies of combustion, okay? So we're trying to show what's the reaction when each of these reacts with oxygen. So I'm going to write my combustion reactions first. So I have C, and we're going to start off with graphite first. When graphite undergoes combustion, which means it combines with oxygen, it produces CO2. And this particular reaction for graphite has a delta H of negative 394 kilojoules per mole. Negative 394 kilojoules per mole. My second reaction, so for a diamond, on the other hand, C diamond, when this undergoes combustion to make CO2, this delta H releases negative 396 kilojoules per mole. So I want to know, what's the energy change when graphite changes to diamond? On this case, I have graphite as a reactant, and I have diamond as a reactant. So in this case, right, it doesn't work. I'm not going to get the cancellation of oxygen and CO2. However, we already did something like this before, actually, when you were, it's escaping me what you did this for. I think it was something with solutions, but I can't think of it right now, but I know we've done it. I want to make sure that my C of diamond is a product. So what I'm going to do, I'm going to keep graphite the same. I'm just going to rewrite that top equation. Delta H is equal to negative 394 kilojoules per mole. But I'm going to flip the second equation because I want diamonds to be a product here. So I'm going to say CO2 forms O2 and C diamond. But if I switch that reaction, the sign of my delta H must also change. So this would be positive 396 kilojoules per mole. So if we see here, if a reaction is reversed, the sign of delta H is also reversed. So let's go ahead and do some cancellations here. Here we go. Let's get a different color. Looks like I have O2 as a reactant in this top one. And I have O2 as a product in the second one. So that oxygen is getting canceled. And it looks like I can do it again, actually, because I have CO2 as a product in this first reaction, and I have CO2 as a reactant in my second reaction. So my sum of these two reactions is that graphite becomes diamond. And in this process, I would take the sum of these two delta H's. So the enthalpy change of this process from graphite turning to diamond would be positive 2 kilojoules per mole. Okay, turning graphite to diamond is an endothermic process. We have to input energy into that system. And we call this Hess's law, manipulating these equations in order to get the overall sum of a reaction. Let's try sample problems 3 and 4, and then we'll be done. Simple problem 2 says, find the delta H for the reaction below, given the following two reactions and subsequent delta H's. So here's my reaction that I want. I'm going to use these two reactions in order to get this net reaction here. So I like to identify reactants and products first. So C2H4O. Looks like I'm going to have to start off with this one right here. So I have C2H4O plus 5/2 O2 yields 2 CO2s and 2 H2Os. And this process, negative 583.5 kilojoules. If I notice this top reaction, however, I have a coefficient of 2. So in order to get this as a coefficient of 2, what I'm going to do is I have to multiply everything in this example by 2. So this would be 2C2H4O. This would be 10 over 2, which gives me 5. This would be 4. And this would also be 4. What is that going to do to my value for delta H? It is going to double. So negative 583 times 2 is going to give me negative 1167 kilojoules. So I multiplied that delta H by 2 because I multiplied all of these coefficients by 2. Let's go ahead and manipulate that second equation. So I see that it looks like I need C2H6O as a product on the other side. So I'm going to flip this top equation. I'm going to flip it, and I get 2CO2 plus 3H2O yields C2H6O and 3O2. Because I flipped that reaction, what is that going to do? That's going to flip my sign for delta H. So it is negative 685. This is going to become positive 685.5 kilojoules. But if I notice I have a coefficient of 2 in front of there, here I still only have a 1. So I'm going to double those coefficients again, just like I did up above. So I'm going to change this to a 4, this to a 6, this to a 2, and this to a 6. And when I double these coefficients, my enthalpy also doubles, and I get positive 1,371 kilojoules. Once I do this, let's do a little cancellation action to see what I have left over, okay? So I'm going to get a different color here just so I can draw some cancellations. Let's do blue. So looks like I'm going to keep this, and I'm going to keep this because there's nothing else to cancel out there. So I have 2C2H4O. And I'm going to skip this one for now. Let's just focus on the reactants, actually. Looks like I have 5 O2s because 10 divided by 2 is going to give me 5 O2s. And it looks like I have 6 O2s over here. So if I have 5 and 6, I have 1 O2 that's left over on this side, actually. So I don't have to include oxygens here. In fact, actually, I'm going to draw my arrow so it makes it a little bit easier. I have 1 O2 remaining on my product side because I have 5 here and 6 here. There's 1 left over. Let's go ahead and look at CO2s. I have 4 CO2s on my reactant side, and I have 4 CO2s here. So they cancel out completely. Let's look at waters. I have 6 water molecules on my reactant side, but I have 4 in my product side. These ones will cancel out entirely, but I'm going to have 2 water molecules left. So that kind of cancels everything out for us. So then I have my O2 on my products, which we already established was left over, and I have my 2 C2H6O. This equation matches this one up here. So I can calculate the delta H by adding these two values together. Negative 1,167 plus positive 1,371 tells me that the delta H for this reaction is positive 204 kilojoules, which means this is an endothermic process right there. Next one's a doozy, but we can do it. Okay, holy moly, look at those reactions. So let's get the black marker out here. So I have diborane is a highly reactive boron hydride, which is considered as a rocket fuel. We want to know what's the delta H for this reaction right here. And I'm given 4 possible reactions, so yikes, okay? I like to try to identify something that's pretty easily recognizable. So I have my 2 borons here. And I actually have 2 borons in this first equation. So I'm going to use this guy. I have 2. I'm going to try to write as neat as I can for this because it's going to be a little much. And I have B2O3. And I'm just going to copy down delta H is negative 1273 kilojoules. I'll notice that I have diboron trioxide as a product in this first reaction, and I don't have that here, okay? So I'm going to have to cancel out B2O3. And I'll notice my second reaction has B2O3 in it. The only thing is that is a product. So I have to make it a reactant by switching this equation. So let's switch it up. B2O3 plus 3H2O. Now we do have to be careful here because there are some differences in states of matter. This is a gas. And this is going to give me B2H6 plus 3O2. My delta H for this, if I flipped the equation, this guy has to be positive. So I'm going to make that, I'm going to change that sign. And if I start canceling here, it looks like I have 2, one of those. Otherwise, I have something here. So 3 O2s and 1.5. So I'd have 3 over 2 left over here. So I have 2 borons plus 3 gaseous water vapor, yields B2H6 plus 3/2 O2. The reason why it's 3/2 is because if I have 3/2 on one side and if I have 3 on the other side, which is technically 6 over 2, right? If I cancel out 3 minus 3 over 2, it's going to give me 3 over 2 again that's left over. So now I'm left with this reaction. A little bit closer, but I have some oxygens and waters to get rid of, okay? Looks like I have to get rid of this water vapor on this side. I need it to be, or I have to get rid of water vapor, okay? And I have water vapor down here. Oops, let me calculate my delta H. And my delta H is equal to positive 762 kilojoules. Now let's get rid of this water vapor. Looks like water vapor is a reactant here, and it's a product here. The only thing is I have to multiply this equation by 3. So I'll do 3 H2Os, liquid, forms 3 H2O gas. And if my delta H, if I multiplied my coefficients by 3, that means I have to multiply my delta H by 3. And I get 132 kilojoules. This cancels out my 3 gaseous water molecules. And I have 2B plus 3 H2O liquid gives me B2H6 and 3 over 2 O2. And my delta H in this example, when I add those two together, would be positive 894 kilojoules. I still have a couple of things to get rid of. I have to add a hydrogen in here, and I have a water, and I have those, and a lot of crazy stuff still happening. Looks like I have to use this equation still. I have to cancel out my O2s, and I have to get rid of this water, this liquid water. So I can actually use this reaction as is, but if I have 3 liquid waters in my reactants here, I have to have 3 liquid waters in my products there. So I am going to have to multiply, my coefficients by 3 again. That should be a 3H2 plus 3 over 2 O2 yields 3 H2O liquid. And that means my delta H for this reaction would be negative 286 times 3, which gives me negative 853 kilojoules. Let's do a little cancellation. 3 over 2 oxygens on both sides. And I have 3 H2O liquids on both sides. Check it out. 2 borons plus 3 hydrogens yields B2H6. This equals my reaction up here. My delta H would be the sum of these two, 894 minus 853 gives me 41 kilojoules. Nice little positive value here. This is an endothermic process. Endothermic. This is what we call Hess's law. Okay, doesn't matter how you get to the final answer. It's path independent. The overall reaction is just the sum of all those individual enthalpies, which is really what you need to know. I know this can be a little confusing. We will practice this in class, so do not fret. Otherwise, I will see you in the next video where we talk a little bit more about the difference between temperature and heat, and we'll dive deeper into thermochemical equations. I will see you then. Bye.